These are the properties of steel. I don't have to do anything special, so click on Add. Then I'm going to define the cross sections. And first I'm going to do only one cross section. I'm going to assume the cross sections are the same for both the members. Okay? So from the cross section type, I'm going to select circular hollow. Okay? And let's try to guess what the inner radius needs to be and what the wall thickness needs to be. So how about 0.1 meters? Is that big enough? Okay? And then how about the wall thickness? We said the wall thickness needs to be at least 20%. So I'm going to set this exactly as 20%. So 0.2 times 0.1. Okay? So this is the only one. So we're not doing R1 and R2. We'll do R1 only first, one design variable. And then we'll modify this and do two design variables. And then we'll see what the trade-offs are.
Why would you get something like that instead of the minimum that it gave you?
You could. Yeah, absolutely. Yeah. With minimum, I'm not sure whether it will satisfy the requirements or not.
Right, probably won't, but...
Yeah.
Okay.
There's nothing wrong with guessing the minimum. Absolutely. Yeah. Okay, next, I'm going to define the nodes. And the bottom left is where node 1 is, so that's where I'll assume the origin to be. So that's 0, 0. Node number 2 is at 0, 3. And node number 3 is at 4, 0. Okay, so again, look at your figure. Bottom left is where the origin is. Origin is at node 1. Node 2 is at 0, 3. Node 3 is at 4, 0. Close, and you'll see those three nodes. And then this is element 1. And this is element 2. And then I must remember that this is a truss, not a frame. So I'm going to convert this into a truss. Okay? And then I'm going to put in the two pin supports. So pin support here, pin support here. And what's the last thing? Applying the load. So I go here, and at node number 2, the Y force is minus 10,000. Okay? So we're done with the model. Now,
You sure?
say that again? Or did I say node 2?
Yeah.
Okay, so let's change this to node 3. Obviously, if you apply to node 2, there will be no forces in the member. Okay, so let's verify. Yes. Okay, so let's analyze this. Okay, so let's say design dash 1. It's done. We have done absolutely no optimization. All we're going to do is check the performance constraints and see whether this design meets the performance constraint or not. So where do we look? We go to View, and we say Element Stress. Is this okay or not? Is this design acceptable or not? Okay, so let's look at element 1. Element 1 is in compression. What's the stress in the element? .9 megapascal, correct? 0.9 megapascal. That's a tiny, tiny fraction of 130 megapascal. So we have over-designed it. Let's look at the second element. 1.2 times 10 to the power of 6, so 1.2 megapascal in tension. Again, that's a small fraction of 135 megapascal. So this is over-designed. Is it acceptable? Yes, it will work. You're paying more, it will work. Okay, so if you don't have a program that optimizes the design for you, what are you going to do? So I'll go back here. And give me some new values to try. 0 point, let's do 0.01 and 0.2 times 0.01. Okay, so let's make a note. We tried with R as 0.1 meters, then we're now trying with 0.01 meters. Yes?
Since we did that first analysis and we saw that one gene has a higher stress level than the other, can we make the assumption that R2 is going to be applied to that gene, R1 is going to be applied to that gene?
No, it doesn't matter. We'll do that. We'll go from 1 to 2 design variables in the next problem. But at the moment, we're assuming both the members are the same radius. The next one will assign a different radius to each one of them. And then it doesn't matter which is 1, which is 2. Okay, so what do you expect? Will the stresses go up or will the stresses remain unaffected? Will the forces in the members change? No, because this is statically determinate. Forces will not change, but my stresses are going to change because I'm changing the cross-sectional properties. Okay, so let's analyze again. It's done. Okay, let's look at the element stress. Oops, 0.01, I'm sorry, 0.01 and 0.01 update. Now let's look at the element stress. Element stress is on. Okay, these designs, are they acceptable?
Yes.
Okay, are we getting able to meeting the requirements? What is the highest stress? 120 or 121 megapascal. That's very close to 130, so we are getting very close to the limit. Okay, so let's stop here and let's see how to use the design features in the program to automatically compute what the optimal value needs to be. So please take notes, and this is the same way you need to do every single problem. So the first step always is to build a model for analysis only. You do the analysis and make sure the boundary conditions, the loads, the geometry, everything is correct. Because if you make a mistake in the analysis model, the design model will give you garbage. It will give you answers which obviously are not correct. Okay, so you start. The only thing after you've done all your analysis is start with the design menu. There is no toolbar. Everything starts at the top and goes down. So start with define parameters. So by parameters, you're going to define everything connected with that problem statement that you wrote, except for the objective function. Okay? So first we'll do the design variables. So this one I'm going to call R1. I'll give it a name. That name can have up to 15 characters. And I don't have to change anything here. The type entity is cross-sectional property. Attribute is inner radius. Group number is 1. So I'll say add. Then I'll do T1, thickness 1. I'll change the attribute to wall thickness. Group number is still 1. I'll say add. Okay, so R1 for inner radius, T1 for wall thickness. We have only one group so far. Next example, we'll do 2 groups. Okay, next, I'm going to do tensile stress. So T stress, tensile stress. Type is element data. Attribute shows up as tensile stress. Element number, I'm going to make it 0. 0 means all the elements. Lowercase 0 means all the lower cases. Okay, so again, if you have any questions, press F1. F1 will bring up help and show you something connected with this.